All right, so let's talk about RSA. Um, RSA is very simple mathematics. The only thing hard about it is that the numbers get kind of big. So when you generate your public key, you have to have two large primes, P and Q. You multiply them together to make N, and then you just pick a number and use it for E. Even a small number like 3 or 5 will do in most cases. And then if you know P and Q and E, you can deduce the private key. It is a little complicated to figure out, but the people who only have access to the public key cannot get the private key because they cannot factor N to find P and Q in any reasonable amount of time if P and Q are large enough. And that's the secret of RSA. The public key does not enable you to deduce the private key, but there is a mathematical relationship, so data encrypted with the public key can be decrypted with the private key. So you go through some examples here. You put in P and Q and then calculate N. And so let me just do some of this. I'm doing it all in interactive mode. You could write programs, but it's not really necessary because the actual math is pretty simple. So here's P, Q, and N, and I'm using, of course, insecure short values just to see the concept. So if 7 and 23 are the prime numbers, and N is the product of those two prime numbers, so this number is not prime, and that's the public key. Now you need to know this phi, which is P minus 1 times Q minus 1, and that's actually the number of values you can use, modulus N, because this is not a prime number, so not all the values are there. P minus 1 times Q minus 1 is the number of actual usable numbers in there. And so you've got this 132 numbers you can use, and now you need a public exponent, which you can use an E equals 5. So when you do that, now you have chosen E, which is part of the public key, the public exponent. So E and N, which is 5 and 161, is the public key people use to encrypt data coming into you. And to decrypt it, you have to find this number D, which has the property that D times E is 1 modulus phi, which means it will get you around all the usable numbers and back to 1. So if I encrypt something with E, if I further multiply it by D, it will now turn into the plain text because that undoes the encryption. So you have to find a D that satisfies this property. So if I do this and I print, say, 20 times E, then 20 times E is, of course, 100 because E is 5. But if I remember, my phi is 132, so I can use modular arithmetic. And if you haven't done modular arithmetic, it works like a clock. I have 0, 1, 2, up to 33, and 66, and 99, and 131. And if I add one more, I'm back to 0. You never find any number except numbers between 0 and 131. And if you have big numbers, you just go around and around the circle many times. So if I wanted that, I would do 20. Let's see if I have phi n in my memory here. I do. So I can print that modulus. The percent sign is modulus. So I do that modulus phi. And that's 100 there. Okay, and now it gave me the right answer and then complained about something. And but I'm not going to worry about that. I'm going to go down here. All right. There. So you can see as I go around, 100, 130 is fine, 131 is fine, and 132 wraps around and gives you 0. So I want to find the number which you multiply E by to get 1. So here I am, 20, 21, 22, 23, 24, 25, 26 is 130, and 27 wraps around, skips 1, and goes around to 3. So I went all the way around the circle, and I missed 1. So I'm going to have to try bigger numbers, like up around 50. And so if I try them, you see I find that 53 times E is 1. So D is 53. That is a number which will undo what's done when people encrypt with E. So now you can encrypt a message. You can only encrypt numbers, but as we know, everything is numbers in a computer anyway. So I want to send this message hi. So I'm going to use a very simple system where I encrypt the characters one by one with ASCII. So a capital H is 72, and a lowercase I is 105, and an exclamation point is 33. So there's my message, 3 numbers. And I just have to take those numbers to the E modulus N, which I can do this way. So this will do RSA encryption. So 151, 119, 157 is the encrypted version of high. And to decrypt it, that X is the plain text, Y is the ciphertext, and D is the decryption key. So since I know that D is 53, to undo that, I can take those numbers to the D modulus N and take them back to 72, 105, 33. So the person who has the private key D can decipher this encrypted message. That's the secret of RSA. And so you can play with it with these small values. You can then decrypt a larger number, and then you can start using some larger numbers. So down here, there's a library to find that D. The process of finding D that I just went through was really clumsy, where you keep trying numbers until you find one. There is Euler's method, which will find it efficiently, and somebody has coded it in this library called SIMPy. So if you install SIMPy and import SIMPy, you now have a function that will do that for you. So you get from here, SIMPy inverse. This calculates the multiplicative inverse on a ring is what it's called, that does this for you. And that saves you a ton of programming and bother. So now you can encrypt things again and send them and decrypt them, and you can then solve a couple challenges here. So encrypt a couple messages and then read a message. And then you've got a message where you only know the public key and you have to crack the public key. And it turns out that you can, in fact, crack a key even this long without taking forever, because the P and Q are close to each other, which is a fairly common mistake people make when setting up these puzzles. So all you have to do is start at the square root and try numbers near the square root until you find a factor. So you can, in fact, crack it. If they were really random P and Q, then it would start to get pretty difficult to crack it here. But if they aren't, then you can find P and Q, you can find D, and you can then read public key encrypted messages. So there's some RSA stuff to try doing.